We're now ready to move on to the next part of this lesson, which has to do with elastic potential energy. We've talked about energy before. We've dealt with kinetic energy. Kinetic energy is the energy that an object has as a result of its motion, and the kinetic energy is 1/2 mv squared. We've talked about gravitational potential energy, is the energy an object has because it is elevated above some level in a gravitational field. The formula for it is m times g times the amount of elevation, y. Now we're going to discuss elastic potential energy, the energy an object has because of deformation. So I have an elastic object. Springs and rubber bands are going to be the most common types of things that you deal with, but it could be any object that is somewhat flexible. Maybe it's hard to flex it or very easy to flex it, but if it resists that flexing, then you deform it and it returns to its original shape. It has elastic potential energy when you deform it. And we say that the elastic potential energy is given by a formula 1/2 kx squared. And we're going to call that the potential energy with a subscript s for a spring. You may see sometimes people will write it with the potential energy with a subscript E for elastic. But whether it's an S or it's an E, it means the same thing. It's the energy of deformation. The K is the spring constant and the X is the amount of deformation. These three kinds of energy are known collectively as mechanical energy. And there will be a theorem that we state a little bit later on that's called conservation of mechanical energy, which basically says that when a system undergoes evolution, when it moves, when there are things, springs or ramps or things like that that the objects interact with, that the total energy of the system is conserved. The mechanical energy of the system is conserved if we can neglect friction. We'll eventually build friction into these systems, but we'll start without friction. Let's make a comment about this force versus displacement curve that we saw just before in the previous section of this lesson. There's a representation of that curve. What that curve says is that the more you stretch the spring, the more force that the spring resists with. And if you find the area under this curve, what you're going to find is the amount of work that's done to stretch the spring. So let's say that I wanted to stretch the spring by an amount that was equivalent to that right there. You can see that I have myself a triangle that has a certain area underneath it. And the area of that triangle is 1/2 of the base times the height. Well, the force is what the height is, and the elongation is what the base is. But Hooke's law tells us that the force is equal to K times X, the spring constant times the elongation. And now when I put all that together, I find that the area of the curve is 1/2 kx squared. In other words, that's equivalent to the amount of elastic potential energy that the spring holds when it's deformed that amount. Here's an example of an application of something we're going to come to call the work energy theorem. When I do work on an object to change its position, in this case I stretch a spring, then I store some energy in that object. In this case, it is stored in the form of the spring's deformation. Say, like when I have a screen door that's got a spring attached to it. I push that door open, I stretch that spring, I deform it. Now the spring can do work for me. I can harvest that energy back. And when I do, that spring is going to close the door. It's going to do some work. It's going to exert a force on the door through a certain distance, and that's going to be able to do work for me. It'll convert that elastic potential energy into the kinetic energy of the door, and eventually, when the door slams, it's going to convert that kinetic energy into sound energy and heat energy until the system comes to equilibrium again. With this background, we're now ready to attack some numerical problems, and we'll look at some examples from your text. The first example is 25.2. For a certain spring, it is found that a 350 Newton force would compress the spring 80 centimeters. How much elastic potential energy is stored in this spring if a 10 kilogram mass is hung on the spring? Well, we've got several things to deal with here. We're trying to figure out the amount of elastic potential energy stored in the spring. And the conditions under which this elastic potential energy is stored is different than the conditions in which we're given information about the spring. We're told that a 350 Newton force compresses the spring by 80 centimeters. I'm going to convert that to meters. We're also told that we want to figure out the amount of elastic potential energy when a 10 kilogram mass is hung on the spring. Now, what kinds of things relate those together? Well, we know that the elastic potential energy equation is 1/2 kx squared, but the x that we're looking for in this case is the x that occurs when the 10 kilogram mass hangs from it, not when the spring is compressed by this 350 Newton force. I also need to know what the spring constant is, K. I don't know that yet, but I can figure it out from this given information. And since they tell me how much applied force compresses the spring, then I can figure out the spring constant from that. So the way I interpret this problem is like this. I've got an uncompressed spring here that has some natural length. But now I exert a 350 Newton force on it. And when I do that, I compress the spring by a distance of 0.8 meters. So from Hooke's law, I can figure out what the spring constant is as a result of this applied force. The applied force is 350 newtons. The distance of compression is 0.8 meters. I'm going to put that into my equation. And now it goes into the calculator, and I get that the spring constant is 437.5 newtons per meter. Now I take this spring and I turn it vertically. And you can think of the same sort of situation that we did when we plotted the graph earlier. So there's my unstretched spring. It's hanging. There's no compression. There's no elongation. And so it's at its natural length. But now I hang this 10 kilogram mass from it, and it stretches. When it stretches, it's going to stretch an amount x, and this x is not the same as the 0.8 meters that we use to figure out what the spring constant is. This x is the amount of stretch when this 10 kilogram mass hangs from it. So I've got to figure out what that x is so I can put it into the elastic potential energy formula. And I'm going to use a free body diagram to help me. So there's the mass. The Earth pulls the mass downward with a force equal to the mass's weight. So the Earth pulls the mass downward with a force of 100 newtons. If the mass is in equilibrium, in other words, all the vibrations have gone out, the mass is stationary, the spring pulls up with a force that's equal to it. That's the spring force. So now I can figure out the amount of elongation from the fact that this 10 kilogram mass is hanging from the spring using Hooke's law. F is equal to kx. I'm trying to figure out what x is. I know what F is. It's 100 newtons. I know what k is. It's 437.5 newtons per meter. So let's figure out what x is. Solve that equation for x and put in the numbers, and now put it into your calculator. I get that the spring stretches 22.9 centimeters or 0.229 meters when the 10 kilogram mass is hanging from it. Now the problem says we want to figure out what the elastic potential energy of the spring is when it's stretched that amount. So I'm going to feed all that information into the elastic potential energy formula. So let's put the numbers in. K is 437.5 newtons per meter, X is 0.229 meters. And I'm going to keep all the decimals in my TI-89 calculator. And now I turn the mathematical crank and out pops a number. I get 11.43 joules. So, reviewing this problem, I had to use the given information to figure out what the spring constant was. Once I knew the spring constant, then I figured out how much the spring would stretch when a 10 kilogram mass was hung from it. I used Hooke's law to help me figure that out, and then I used the potential energy formula to figure out how much energy was stored. That's one example. Let's move on to another. Example 25.4 reads this way. A 40 kilogram mass was set on a spring whose spring constant was 800 newtons per meter. A. How far was the spring compressed? B. How much elastic potential energy does the spring possess as a result of the mass being placed on it? And C. How much work was done on the spring? let me make a note here about on the spring. I've emphasized that because sometimes you'll be asked questions about how much work was done on something or how much work was done by something. Let me remind you that work is equal to force times distance, and generally the work that's done on the spring and the work that's done by the spring are going to be equal in magnitude, but they're going to be opposite in sign. And so the sign is going to depend on what the direction of the force is with respect to the displacement. Work is equal to the force times the displacement. If those forces and displacements are in the same direction, I'll have a positive amount of work. If they're in opposite directions, they'll have a negative amount of work. Let's solve this problem. So here's a poor drawing of a spring that is uncompressed. Your textbook actually has a diagram, which I have not reproduced here, but I'm sketching it. Here is my uncompressed spring. Now I take and set a 40 kilogram mass on it. And I want to know how far is the spring compressed. I'm going to call that amount of compression y. Now I didn't do that in the previous problem. I could have when we had vertical things, but I generally like to make my variables go with the directions. So I'm going to make this y. And we're going to say that the amount of force is equal to k times y. So the spring is pushing with that amount, and it's balancing the weight. So from a free body diagram, I'm going to see that the spring force and the weight are in opposite directions. The earth pulls the weight downward with a force of mg, which is going to be 400 newtons. So the spring force is going to resist that with a force of 400 newtons as well. The spring force is 400. And we're trying to figure out the amount of compression. We're trying to figure out what y is. So I'm going to solve this equation, Hooke's law, for y. And now I'm going to put in the numbers. They told me what the spring constant was. I can do that in my head. That's equal to half a meter. The amount of compression is half a meter. That's part A. Now we want to know part B. How much elastic potential energy does the spring possess as a result of the mass being placed on it? I'm going to use the potential energy formula. I know what the spring constant is, and I know how much the spring is compressed, 0.5 meters. So I'm going to feed those numbers in. And now they go into my calculator. Some people can do this in their heads. I get 100 joules. Now, part C. How much work was done on the spring? Now, you might think I could say that the work is equal to the force times the distance. And that's true as long as the force that's doing the work is constant. But in this case, that force is not constant. When I compress the spring a little bit, I get a little bit of force. If I compress the spring more, there's more force that's being exerted. And so that force is increasing as I compress the thing more and more. So this formula is true only when the force is constant. The spring force isn't constant, so I can't use this work formula. Here's an aside to calculus students. You could actually integrate this if you wanted to. I'll leave that as an exercise for you calculus students, but we're not going to worry about that. So what am I going to do? I'm going to employ something called the work-energy relationship, which says that the amount of work that's done on the system is equal to the change in the energy of the spring. And that change in the energy is in the form of the elastic potential energy. And that change in the elastic potential energy is equal to the final elastic potential energy minus the initial elastic potential energy. The initial potential energy was 0 because the spring wasn't compressed. The final was 100 joules because that's how much we calculated in the earlier part. So the work that's done is equal in magnitude to the amount of energy that's stored in the spring, 100 joules. Now let me return to this note that I said earlier about the work that's done on the spring. The force that's doing the work on the spring is in the same direction as the spring's displacement. In other words, I am pushing downward and the weight that's doing the work is also moving downward. They're in the same direction. This is a positive number. That finishes this example. That's it.